Okay, this is Lecture 9, Part B, and we're going to cover these three topics at the bottom of the outline. You should have already watched Part A. To understand how sediment moves through a river system and out through the river itself, a sediment budget is a really useful tool. And you can see the definition down here. A sediment budget is an accounting of where is the sediment coming from? What are all the specific sources? How does it move through the watershed? Does it get stored in between? And then how much leaves the watershed? This diagram here in the upper left shows an example of a sediment budget. And the sources are grouped into types of sources. So of all the sediment that comes into the river system, about 70% of that is sediment that comes from upland erosion. Another 20% is sediment that comes from tributaries. And then the remaining 10% is sediment that comes from landslides. So this represents 100% of the sediment volume that goes into the river system. And then what happens to that sediment as it moves through the river system towards the outlet of the watershed? Well, some of it that was eroded off the hill slopes didn't even get in the river system. It was deposited as colluvium at the base of the hill slopes. In this case, that's about half the sediment. Another 30% does get into the river system, but then is deposited in the floodplain and in terraces down on the floor of the valley. And of all the sediment that got eroded and mobilized, only about 20% of it actually was transported out of the river system. Let's look at an example of a sediment budget, and we're going to look at a really big one, the Mississippi-Missouri River system. This very large river basin that occupies the center of the U.S., and it has these major branches like the Ohio River, the Arkansas River, the Missouri River, and so on. This river flows out into the Gulf of Mexico in Louisiana, past New Orleans, and it's a major sediment provider to the U.S. coast of the Gulf of Mexico. And sediment from the Mississippi River and the Missouri and its tributaries is really the sediment that has built the beaches and the coastlines of all of the Gulf Coast from Texas to Florida. And it's also fed the delta of the Mississippi River. This is the sediment that's actually building that lower part of Louisiana out into the Gulf of Mexico. Historically, this river system carried a lot of sediment, particularly from the Missouri River, which drains drier parts of the Great Plains where there's a lot of natural soil erosion. Starting in the early 20th century, dams were built on the Missouri River was modified to make riverboat navigation possible, and then eventually dams were built in the middle 20th century on the upper Missouri River to provide water and control the flow of the river and provide flood control. So as a result, the sediment budget of the Missouri River system is really significantly altered. Here are two sediment budgets for the Mississippi-Missouri system. The one on the left is before dams went in, and the one on the right is after dams went in. The thickness of the brown line indicates the volume of sediment moving through the river. What you can see on the left is that the Missouri River has the thickest line in the upper part of the basin, and the Missouri River was really the main sediment source. The Mississippi River is this little stub right here. So the upper Mississippi River in Wisconsin and Minnesota and Iowa really wasn't a big sediment producer. Similarly, the Ohio River over here also was not a very big sediment producer. And if we look down at the volume of sediment down in the Gulf of Mexico, we've got a really fat, wide line, a lot of sediment coming in, and most of it coming from the Missouri. After the dams went in here on the right, we see how shrunken all those lines are. The Missouri River itself is really significantly smaller. We begin to see that the other branches now are contributing some significant sediment, partly from agriculture and simply because they aren't as dammed as the Missouri. So if we look down at the Gulf of Mexico down here, the line is much thinner, and total sediment sent down to the delta was reduced by about 70% as a result of damming. The result is that there was less sediment available to maintain the beaches. The beaches started to erode. There was less sediment to feed the delta itself and the wetlands in the delta, and the wetlands began to sink and become more flooded and more waterlogged. And a lot of the damage of Hurricane Katrina has been attributed to losing that coastal buffer system that would have been a buffer between high water levels with a storm and strong waves that would have kept the storm water from flooding into the settled land if we had had a healthier, more robust system of beaches and wetlands in the Mississippi-Missouri system down at the Gulf of Mexico. And so this loss of sediment due to dams is having significant effects down in the delta. This kind of sediment budget analysis is really useful for a lot of river management questions. Looking at sediment budget change over time helps us understand river sediment dynamics and helps us explain why some parts of a river system might be aggrading or degrading. Some parts might be aggrading and other parts might be degrading. The sediment budget can help us figure that out. Sediment budgets are also useful because they really tell you what are the particular land uses and what are the areas where most of the sediment is coming from. And these coastal sediment budgets obviously are really important in understanding coastal erosion from storms and subsidence along coastlines as marshes sink into sea level. They're used a lot in developing water quality management plans because sediment is a major pollutant that degrades water quality in a lot of agricultural areas of the country. And they're also just useful as tools for thinking about how to develop land in the future. Okay, let's look at several terms related to erosion and sediment loss from a watershed. We're going to start with soil erosion. Soil erosion refers to the amount of material lost from a plot or a particular place on a hill slope, often an agricultural field. It's fairly small scale. It's not measuring the whole watershed. Soil erosion refers to a plot or a field. It's measured in the field. There are ways you can sort of collect the sediment running off of a small area or other instruments you can use. It's often done for managing agricultural land uses. The units for soil erosion is weight per area per unit time. So this might be tons per square kilometer per year or tons per acre per year. And so the way it's measured is either direct measurement in the field or cesium-137. You might remember from Chapter 2, cesium-137 is one of those radionuclides from atmospheric atomic bomb testing. It's radioactive. It has a short half-life, so it's good for doing numerical dating of relatively short time spans, and sometimes it's applied to soil erosion. The second major concept we want to look at is sediment yield. Sediment yield is a measurement of sediment transported out of the watershed by the river. It's measured in the river water, whereas soil erosion is measured up on a plot or a field somewhere in the watershed. Sediment yield also usually refers to relatively short-term modern measurements, so measurements made over the last decade or a few decades. We're measuring the amount of sediment that the river is carrying out of the watershed, so it's integrating erosion and deposition over the whole watershed, whereas soil erosion is really site-specific. Sediment yield is, however, measured in the same units as soil erosion. It's measured in weight per unit of land area in the watershed per unit time. And it usually only includes the solid sediment, not the dissolved rock. Now, if we were to go out to a medium watershed and measure sediment yield at several plots around the hillside, measure soil erosion at several plots around the hillside, and then measure sediment yield leaving the watershed down at the mouth, in almost all cases, we're going to find that the soil erosion rate is larger than the sediment yield rate. More tons per acre being eroded in the fields than tons being transported out of the watershed. Why? Think about that for a minute. Well, the reason is that some of the sediment that gets eroded off the hillside is not going to make it all the way to the river channel. Some of it's going to be deposited in colluvium at the foot of the hillside or in landslide deposits, and only a certain percentage of it leaves the watershed. Go back a couple slides to the sediment budget and you'll see an example of that. So now a third major term that relates to erosion and sediment yield, and that's denudation. Denudation is the long-term view. And when we talk about denudation, what we're thinking about is how rapidly is the land surface eroding down in this watershed over geologic timescales. So denudation rates are usually we're thinking about thousands of years, hundreds of thousands of years, maybe even millions of years. And the unit is the depth or thickness of material that's removed per unit time from the land area. Now, some parts of the watershed will be eroding faster, some will be eroding slower, but denudation is the average thickness if we average all those different points over the whole watershed area. And so the units are going to be millimeters per year or millimeters per 1,000 years. And these rates usually include both the solid sediment that's coming off, but also dissolved material from chemical weathering. How do we measure denudation? Well, denudation rates can be estimated using these direct measurements of modern processes that we've been talking about, but we recognize that those denudation rates that we measure today that are right for this decade don't necessarily represent geologic time, because land use is really different today and climate is really different today from what it's been over long-term geologic time. And so dating techniques like cosmogenic isotope dating of bedrock is a technique that's really useful for this, and that was discussed back in Chapter 2. So denudation rate answers the question, how rapidly is the continental surface being lowered by weathering and erosion? But don't forget, in terms of elevation change, what goes down also comes up. So denudation is countered by tectonic uplift, and denudation is also countered by isostatic uplift. So what are some typical denudation rates? Well, in the mid-latitudes, typical dates are a few tens of millimeters per 1,000 years. So typical rates of maybe 20 up to 150 millimeters per 1,000 years. What does that mean? Well, 20 millimeters per 1,000 years means that over 1,000,000 years, the land surface will lower 20 meters. So we get a sense of what timescales does it require to have some substantial decrease in the rock mass in the watershed. These denudation rates vary from place to place, and most of the variation of denudation rates is related to relief. Steep mountain areas have high denudation rates, flat plains have low denudation rates, and runoff. Areas that get a lot of rain have higher denudation, dry areas have lower denudation rates. We don't have a lot of data on global denudation. We have data from different sites here and there, kind of spread out around the world, but this is still a topic that's not really well understood yet. Here's a map that shows patterns of global sediment yields, not denudation. We're talking about short-term measurements now. Global sediment yields around the world. And you can see from the colors in the legend that red is really high rates of sediment yield per square kilometer. And then we go down through the browns and the yellows, and green is low rates, and white is essentially none, or at least they can't measure it effectively. And if you look at this map, you see that what I just said in the previous slide holds true. The highest rates are in the mountainous areas of East Asia and Southeast Asia. The Himalayas and the mountains of Southeast Asia have the dark brown color, so they're quite high. If we go over to the Americas, the Andes in South America have high rates, and the mountains in southeastern Alaska, southern Alaska, where we have steep mountain ranges and we're in a marine climate with a lot of water delivery, we have high sediment yield rates. Once we get outside those dark brown areas, you can see most of the U.S. is kind of intermediate in its erosion rates. It's pretty low in the Pacific Northwest, kind of green colors, and that sort of tan in the Great Plains. So this slide shows sediment yields from major rivers in the world, and you can see the Amazon River here coming out of South America. You can see the South Asian rivers, the Ganges and the Mekong here coming out of South Asia, and you can see which places have the highest, big river basins that are also draining regions that have high soil erosion and sediment yield. The Yellow River in China is another major sediment source in the world. So in this case, we're thinking about individual river basins. And you can also see that there's a lot of parts of the world that have pretty small values, surprisingly small. This is another way of looking at those data on river sediment yields. And so it's a plot of individual rivers. And if we look down here at the bottom, the Brahmaputra is the largest one. Its sediment yield is all the way out here at about maybe 1,700 tons per square kilometer per year. And there are two bars plotted for the Brahmaputra. There is one here on the left side that represents the solid sediment load to the red line, and then there's another one on the right side that represents the dissolved sediment load. So how many tons of rock material is going down the Brahmaputra in terms of dissolved mineral components of rock. And so we see the Brahmaputra is the bigger, the Yellow River in China is the next, the Ganges in South Asia. And so we see this long list of rivers going up here. We don't get to anything in North America until we get to the Colorado. So that drains a pretty dry desert plateau area that is very erodible. The Mississippi River is kind of up here in the middle. It's not really a very big one. And well, you can see the different rivers as we're declining around the world. But one of the important messages in this figure is how important is the solid sediment load versus the dissolved sediment load in terms of amount of material being moved off continents. And you can see that the solute load is, in almost all rivers, it's a small fraction of the solid sediment load. So solid sediment load is bigger than dissolved load. Okay, one last topic we want to cover in this lecture, and that is the geomorphology of channel networks. So channel networks are another way of looking at river basins, and in this case we're looking at the lines of flow that flow into each other and join and continue downstream to flow out of the watershed. What about the network itself? What are the characteristics and size and scale and properties of the networks? This is a picture from a satellite from orbit, and we're looking down at an arid part of the Arabian Peninsula to a fairly desert plateau. And what we see is a drainage network incised into that rock plateau. And you can see many individual little tribs, first order tribs, coming together and flowing downstream and joining. And you can see that it's a dry channel network in this case. It only carries water occasionally, but you can see the channel getting larger and wider as it continues downstream and continuing to gain small tributaries even after it goes downstream. Just for comparison, here's a channel network on Mars. It looks very similar to the channel network we saw on Earth in the previous slide. So it's physical laws and processes that are determining how networks form, how tributaries join together, the number and scale of tributaries that a certain branch of the river will have, and what their geometry is to each other. In figure 7.4 in your reading, we can see different geometries of channel networks that reflect different geologic structure. The one at the top, dendritic or tree-like, occurs where you have a relatively homogeneous geology underlying the watershed, and it's just the most efficient network shape to get water off the watershed. It's the most common type of drainage pattern. As we go down to the two in the middle, we can see trellis and rectangular that are both pretty strongly controlled by geologic structures. So if we have a series of geologic folds or faults that are running parallel to each other, the rivers are limited and they tend to have these long, narrow drainage basins with short tributaries coming in at right angles, and that's called trellis, long straight streams with short tributaries. Another kind of geologic control is rectangular. If we have a landscape where the underlying bedrock has strong joints and fractures that are running in particular directions as a result of geologic stresses that have been applied to them over long periods of time. So you might have one area where it's got a set of joints that run northeast, southwest, and then it has another set of joints that run more east-west. And what you're going to find is you'll find a lot of sections of the drainage network that are going to be in one of those two orientations, and very few pieces of drainage network that are at any other orientation. And so the rivers kind of occupy those patterns of joints. And the example you see here in the figure is two sets of joints, and they're at right angles to each other. It's like one set's running north-south and the other set's running east-west. And so you get these very rectangular shaped drainage networks. And then finally, where you have a central peak, drainage flows away from it, and this is called radial. And of course, that's the drainage network that is shown on the University of Oregon Great Seal. Okay, that's the end of Lecture 9, and next you're going to view Lecture 10. Lecture 10 covers the rest of Chapter 7, Fluvial Landforms. Lab sections are going to meet this week, and you're going to identify and measure fluvial landforms using the national map. So you want to bring your computer if you can. You'll have to make some simple calculations. So if you have a calculator on your phone or a calculator on your computer or pad, that would be useful. And of course, Test 1 is coming up on February 9th, and a study guide for Test 1 is going to be posted on Canvas. The question types in Test 1, there'll be 3 types of questions. We'll start with some definitions, and I'll ask you maybe 5 or 6 terms to give me a definition for. When I ask you for a definition, I want a really good definition. I want a term that distinguishes that scientific concept from other related scientific concepts. So if I said meandering channel, you could say a type of river pattern. But that's not a complete definition because it doesn't explain to me how meandering is different from other types of river patterns like braided or straight. The second kind of question is going to be multiple choice. That's pretty straightforward. You know what those look like. And then finally, there'll probably be kind of a short answer or essay section where you'll have a few questions where you actually are going to write out longhand your own ideas and thoughts on that question.